All right, we are starting with an iClicker, so the class has started. Please join on iClicker. I know you all have taken an bio exam or are about to. If you're about to, good luck. Let's focus on chemistry for the next 50 minutes, and then after class, you can talk about whatever you want to talk about. But let's try to focus while we're in class here today. Got some announcements for you. Soon. All right, again, please join on iClicker if you haven't already. Some announcements. My office hours today are canceled, but Professor Cunningham teaches another section of Chem 1070. She has office hours just for any general chemistry class today from 2 to 4 p.m. And that's in 117, which is just across the hallway. It's a big conference room with the glass windows. So if you have questions, you want to stop by and get those answered today, you have Professor Cunningham. She's very nice. She'll help you out with Gen Chem. And then I have an added office hour tomorrow at 2 o'clock, and that's in my office, which is upstairs. Remember that our midterm is Friday, so it is 30 questions. It is cumulative, so it covers chapters 1 through 4, and it will be all multiple choice. The chapter 3 and 4 learning curves are available on Achieve. If you'd like to complete them for extra credit, they're due at the end of the day, Friday. They are a good review for the midterm, so if you're iffy about completing them, I recommend that you do. It's a good review. They're all multiple choice questions, so you get used to answering some multiple choice. And then no Achieve due on Monday, so nothing to worry about after the midterm on Friday. We'll have the next Achieve due the following Monday. And then over the weekend, I will have, probably over the weekend, I'll have the second half of Chapter 5 PowerPoint posted. I'll let you know when that's posted so you can have that ready for class. Questions about any of this? Okay. Then the next slide is that question that not this one. So before we start this, in class on Monday, we talked about mole conversions using a balanced chemical equation to determine how much product is reacted with another product, or how much reactant is reacted with another reactant. So that's what we did in this first question. We had a certain amount of moles of oxygen, and we were determining how many moles of aluminum would react with that amount of oxygen. So we've already gone through this one. We did another reaction looking at moles of HCl used and how many molecules of hydrogen gas would be produced. And then here we are going to do an iClicker. So you'll work on a question for a few minutes. Let me get this started so it gets sent to all of you. The first iClicker question, so two are going to come to you. The first one is determining the balanced equation. So review for Friday, there is one, maybe two, there's a few balancing equation questions. So we've got some balancing review here. The question says that we have a sample of 0.712 moles of KClO3 that's heated gently for a time. Of that amount, 0.1146 moles is decomposed into KCl, potassium chloride, and oxygen gas. So we can write out the balanced equation. Well, the unbalanced equation we'll do first. And so your first task is to balance this equation, and then your second task is to calculate number of moles of oxygen gas produced. So let's spend a few minutes working on that. In the iClicker slide, KCl is represented as a solid, but it is aqueous. That was a mistake when I put the slide together. So you have a total sample of the 0.1713, but of that sample, only 0.1146 decomposes, so that's only about that's actually
Oh, yeah.
right. We would have some reaction. If you're already done in a few slides in section 5.2, you'll also be balancing an equation. You could get started on that, but we'll spend a few more minutes here. Two more minutes. You know, if you're stuck. Oh, I forgot to mention that. When you submit, if you already submitted, the second one is fine. But the way iClicker is accepting the answer is just the number. I'll accept it. Don't worry. But if you haven't already, do me a favor and just put the number in. 30 seconds. Get your answers submitted here. I'll give you 20 seconds. At least have the first one answered if you don't have both. All right. Let's see what we're thinking. Mix for the second question. Not too bad for the first one. So let's balance this equation. We have 1 potassium on the left, 1 potassium on the right, 1 chlorine on the left, 1 chlorine on the right. But we have 3 oxygens on the left and 2 oxygens on the right. So we need to find the least common or the lowest common multiple between 3 and 2. That's 6. So we should add coefficients so that we have 6 oxygens on the left, 6 oxygens on the right. So we need a coefficient of 2 in front of potassium chlorate. So now we have 6 oxygens on the left, coefficient of 3 in front of oxygen gas, 6 oxygens on the right. So we have our oxygens balanced, but now we have 2 potassiums on the left. We need 2 potassiums on the right, so we add a coefficient of 2 in front of potassium chloride. And then now we have 2 chlorines on the left, 2 chlorines on the right. So we're all set with balancing the equation. Now the question says we have a sample of 0.712 moles of potassium chlorate that is heated for some time, and 0.1146 moles of the compound decomposes. So if only 0.1146 moles decomposes, that is all that is reacted to produce oxygen gas. So we use that amount, 0.1146 moles of KClO3. That is the amount of moles reacted. And then now we, based on the coefficients from the balanced chemical equation, we can say if we have this many moles of potassium chlorate, how many moles of oxygen is produced. Well, the ratio from the equation is that for every 2 moles of potassium chlorate, 3 moles of oxygen is produced. And so we use that as a conversion. 3 mole of O2 is produced for every 2 moles of KClO3. And that's all we need to do. We cancel out moles of KClO3. We have moles of oxygen, and that's what we're looking for. So if you solve this equation, we have, where are we? 0.1719 moles of O2 produced. If you're just going from moles to moles of a reactant to a product, all you really need is that balanced chemical equation, and using the coefficients as that ratio will give you the correct amount of the other substance. So that concludes this first section, just using mole conversions. We use the coefficients in the balanced chemical equation to convert between moles of one substance to moles of another. And those are our reacting ratios. So now in this next section, we will be doing similar equations, similar math problems, but will involve the mass of reactants or mass of products. So if we know the mass, we can determine the moles of a substance using its molar mass. So remember the reacting ratios or the ratio of coefficients in a balanced chemical reaction, that is a mole ratio. So we can only use the ratio if we already have mole amounts of the substance, and that will only give us mole amounts of another substance. So if we start with the mass of a reactant, for example, before we can find how much product is produced, we need to use the molar mass of the reactant to convert between masses and moles, convert to moles. So in this figure, this is in the book, we've expanded the center of this, which was on a previous slide in section 5.1. Now, if we don't have moles of A, but we have mass of A, then we can use the molar mass of A to find the moles. And then if we have mass of B, we can use the molar mass of B to find the moles of B, and then you can do any conversion between moles of substances in a chemical reaction. We'll do an example of this on the next slide, but the first part is balancing the equation, and that just the balance part will be the iClicker, so let's do that first. If you've balanced it, go ahead and start trying to calculate the amount of solid phosphorus. No, let's see. No, the amount of chlorine gas that will react with a certain amount of solid phosphorus. Say 1 more minute. Okay, looks like almost everyone's in. I'll give you all 10 seconds. All right. Not too bad. So, trying to balance the equation, we have 2 chlorines on the left, 5 chlorines on the right. We have 1 phosphorus on the left, 1 phosphorus on the right. So that one's balanced, but we're going to have to use coefficients to balance the atoms of chlorine. Again, we have to use the least common multiple between 2 and 5, and that's 10. So we'll need to add coefficients to have 10 chlorines on the left, 10 chlorines on the right. For Cl2, we need a coefficient of 5. And for phosphorus pentachloride, we need a coefficient of 2. So now we have 10 chlorines on the left, 10 chlorines on the right. But now we have 1 phosphorus on the left, 2 phosphorus atoms on the right. So we need a coefficient of 2 in front of phosphorus reactant. So we've taken care of step 1. We've balanced the chemical reaction. Now we need to do our stoichiometry to find the mass of chlorine gas reacting with 2.8 grams of phosphorus. So, are there any questions before I move on? Okay, so we start with 2.80 grams of phosphorus. And we want to end up in mass of chlorine. Well, we can convert moles of phosphorus to moles of chlorine using the balanced chemical equation, but we need to first convert grams of phosphorus to moles of phosphorus. So we can do that by using its molar mass, and that's just the molar mass of 1 phosphorus atom. So 1 mole of phosphorus is 30.974 grams. So using its molar mass, now we know how many moles of phosphorus are reacted. Now we want to find moles of chlorine, so we can use now the molar ratio from the balanced chemical reaction. For every 2 moles of phosphorus reacted, 5 moles of chlorine gas are reacted. And this is just the coefficients in the balanced chemical equation. So far, we have calculated the amount of moles of chlorine that's reacted with the amount of phosphorus that was provided to us in the question statement. But we're looking for mass of chlorine gas, so we need one more step converting moles of chlorine to mass of chlorine using its molar mass. So molar mass of chlorine gas, we look at the periodic table. For the mass of chlorine, multiply it by 2 because we have 2 chlorine atoms. Before we calculate the final answer, we can go back and make sure that all of our units cancel out and we end with grams of chlorine because that's what we're looking for, grams of chlorine. So we start with grams of phosphorus, and we have canceled out the unit grams of phosphorus by using molar mass. And we have moles of phosphorus. We're canceling out units of moles of phosphorus by using the balanced chemical equation, that molar ratio. That gives us moles of chlorine. Cancel out units of moles of chlorine by using the molar mass of chlorine. So we're ending with units of grams. If you calculate all of this, you should get 3.03 times 10 to the 4th grams of Cl2. So you could do one equation at a time. So convert grams of phosphorus to moles of phosphorus, find the value. That's moles of phosphorus. Then convert moles of phosphorus to moles of chlorine, find the value. Moles of chlorine, continue on. I like to put everything in one equation because then you don't have to worry about sig figs along the way. You don't have to round along the way. Because if you round too early, that can impact the final answer. So in your calculator, you could do 2.8 divided by 30.974. And then whatever that is, multiply by 5, and then divide by 2, and then multiply by 70.903. You'll get your final answer. Yeah.
Can you go over this one more time? Because when I do the equation, I'm not quite getting the sense.
Okay. Do you have, are all of the values through the same?
Yes.
Anyone else get any different number? Wow, I got this from the book. I didn't calculate it on my own. Let me make sure I have everything the same. No, you're right. It is 16. I was looking at the next one. You're right. Thanks, everybody. This is 16.0 grams of Cl2. That was extremely off. I was looking at the wrong slide. We do have one more example, and I put the answer for that next one. Thank you. Appreciate it. So on that note, let's go to the next question. We're doing more stoichiometry. I'll give you all a minute to get started, and then we'll do it together. It's not an iClicker. But we are calculating the mass of chlorine in grams that can be produced by the electrolysis, so we're doing an electrolysis reaction, of 50 kilograms of sodium chloride. So if we start with 50 kilograms of sodium chloride, how many grams of chlorine gas can be produced? So get started. I want you all to have a minute to kind of wrap your head around the question. Careful with units. And then we'll use a similar process. We need to convert to moles. The first thing we always do is make sure our chemical equation is balanced. This one is already balanced, so you don't have to do any balancing. You just need to calculate. All right, let's start going through this one together. What's the first thing we do here? Convert to grams. Yeah, why do we have to convert to grams? We have to calculate mass of chlorine in grams. The other reason? All of our molar masses are in grams. So if we want to convert mass to moles, we better be starting with grams of the substance. So we have kilograms of sodium chloride. We need to convert that to grams. You could do 1,000 grams are in 1 kilogram, or 10 to the negative third kilograms is 1 gram. Either way, you have the same conversion factor. So we're converting kilograms to grams. Then we need to convert grams to moles. We use a molar mass of sodium chloride. Finding the molar mass of sodium chloride, we add the atomic mass of sodium to the atomic mass of chlorine. So 58.44 grams. Now what do I do? Molar ratio. What molar ratio do I use? 1 mole of chlorine to 2 moles of sodium chloride. So we're trying to find mass of chlorine gas. We're starting with moles of sodium chloride. For every 2 moles of sodium chloride, we produce 1 mole of chlorine gas. So now we're in moles of chlorine. We want to find grams of chlorine, so our last step is converting moles of chlorine to grams. We use the molar mass of Cl2, which is 70.903 grams. And this is the equation where the final answer is 3.03 times 10 to the 4th grams of Cl2. Oops. Questions on this process? Okay. Well, that brings us to the end of section 5.2. So 5.2, we're doing molar conversions, but now we're involving mass. So we need to convert to moles in order to use mole ratio. Then we convert to mass of anything else. In 5.3, we will now be working with quantities of reactants where we have one that's a limiting reactant and one is an excess. So far, all of the calculations that we've done in this chapter, we've been assuming that we have sufficient amounts of all reactants. But this isn't always the case. So if we have one reactant that is used up before another, this reactant limits the amount of any other reactant that can react, and it limits the amount of product produced. We call the reactant that limits the amount of product produced the limiting reactant. So just some terminology on this page. The reactant that is used up first is the limiting reactant. And we say it's present in limiting quantity, not quality. So that's our limiting reactant. Any reactant that is left over after a reaction, we say that reactant is an excess. So we have excess amount of the other reactant. And then we can say the reaction has gone to completion when the limiting reactant is used up. Once the limiting reactant is used up, there's no more of that reactant left over. The reaction cannot proceed. You've made as much product as you can. This next slide, we have one of those particle pictures to demonstrate a reaction where we have a limiting reactant. So this reaction is a combination reaction of nitrogen gas, hydrogen gas, and we form ammonia. If we have, let's say, 4 moles of nitrogen gas and 6 moles of hydrogen gas, we can only produce 4 moles of NH3. The amount of hydrogen is limiting how much NH3 can be produced. all of the hydrogen is used up and we have excess nitrogen left over. So our hydrogen is the limiting reactant, nitrogen is the reactant in excess. So let's do some calculations that aren't involving chemistry, but we still have some limiting factor. I'll use the general term factor. We have some limiting factor in these equations. So let's say we want to purchase some coffee beans. They cost $8 per pound. How many pounds of coffee beans can be purchased with $108? Well, if we start with $108, and 1 pound of coffee costs $8, then we can purchase, if we calculate that, that's 13.5 pounds of coffee can be purchased. If we assume the store has an unlimited amount of coffee, then in this scenario, our limiting factor is the money that we have, the amount of dollars. We can only purchase 13.5 pounds because we only have $108. But now let's say we still have $108, but the store only has 12.5 pounds of coffee in stock. Well, even if we have $108, we can only purchase 12.5 pounds because there are only 12.5 pounds available. So the amount of coffee now is limiting. The amount of money is in excess. You'll have some money left over after you purchase the 12.5 pounds, which is all that's available to purchase. When we are solving limiting reactant problems in chemistry, we have to first determine which reactant is limiting. So you'll have multiple reagents, you'll have the quantities of those listed, and you need to determine which is limiting. And then we base all of our calculations on the limiting reactant. And there are 3 ways to identify what's limiting. We're going to talk about the first 2 really, but you could separately calculate the amount of product that could form from each amount of each reactant, and then whichever reactant produces less product, that's your limiting reactant. You could divide the moles of each reactant by its coefficient, and whichever quotient, the result of that, is smaller, that will tell you what the limiting reactant is. Or you could find the amount of each reactant needed to completely use up the other reactant and then ignore the scenario that requires more of a reactant than what is actually present. The third one requires more steps, so it's not that useful. We're going to talk about the first 2 methods. So here's a scenario. We have the first molecule, CH3OH. The name of that is methanol. I don't necessarily expect you to know the name, but I will say the name methanol. That's CH3OH. That's reacting with oxygen gas. We form CO2 and H2O. By the way, what type of reaction is that from previous units? It's a combustion reaction. We have a carbon, hydrogen, oxygen containing compound reacting with oxygen gas. We form carbon dioxide and water. It's a combustion reaction. And then it tells us we have 1.5 moles of methanol, 0.5 moles of oxygen. So let's do method 1, where we take the amount of each reactant and see how much of a product can be produced. We find which reactant produces lower amount of product. So let's start with methanol, 1.500 moles of methanol. Using our balanced equation, let's just calculate the amount of carbon dioxide produced. You could do water, as long as you're consistent when you're comparing each reagent, it doesn't matter. But we'll do carbon dioxide. So now we use our molar ratio. 2 mole of CO2 is produced for every 2 moles of methanol. So that means 1.500 moles of methanol would produce 1.500 moles of CO2. So if methanol is our limiting reagent, then we will produce 1.5 moles of CO2. Now we need to check with oxygen. We have 0.500 moles of oxygen, we produce 2 moles of CO2 for every 3 moles of oxygen. And so 0.500 moles of oxygen will produce 0.333 moles of O2. So from method 1, we're calculating the possible amount of, this should be CO2 at the end there, of CO2 produced from each amount of each reactant. We see that 0.5 moles of oxygen gas produces fewer moles of CO2. So if we have 1.5 moles of methanol and 0.5 moles of oxygen gas, we can only produce 0.333 moles of CO2. So that tells us that O2 is the limiting reagent. And then methanol, CH3OH, is an excess. We will have extra methanol left over. So that's method 1, just finding the amount of moles of some product based on what is present in the reactant amounts. I'll give you all a second before we start method 2. I see a lot of you writing. Okay, method 2, we take the amount of moles of each reactant and divide it by its coefficient. So for methanol, CH3OH, we take the amount of moles, 1.500, divided by its coefficient, which is 2, and that gives us a number, 0.7500. We do the same thing for oxygen gas, O2. We take the amount of moles, 0.500, divided by 3, and that gives us a quotient of 1.167. Of these two numbers, 0.167 is lower, so that tells us that oxygen is the limiting reactant. So both methods will tell you which reactant is limiting. This is a quicker and simpler method. This one is useful if you also need to determine how many moles of a product is produced. Then you're already kind of starting that calculation here. But you can always use either method just to determine which reactant is limiting, and you'll be able to determine which is limiting by either method. Questions on this before we do an example? Okay, let's go to this next page. We are calculating the number of moles of reactants and products present after the reaction of 1.500 moles of methanol and 0.500 moles of oxygen. We have the same reaction in the same amount of reagents as the previous slide, so we already know which one is limiting. We already know O2 is limiting. If you were given this question and you hadn't done the previous slide, you would need to first determine which reagent is limiting. So let's just write a note from previous slide. Okay, so we know O2 is limiting. And this question is only looking for a number of moles. So we can determine how many moles of carbon dioxide are produced, how many moles of water are produced, and how many moles of methanol are reacted we have to base all of that on the amount of oxygen present. So if we have 0.500 moles of O2, let's just find the amount of CO2 produced. We already did this on the previous slide, but we'll rewrite it again. We have 2 moles of CO2 produced for every 3 moles of oxygen. So we have 0.333 moles CO2 produced. To find the amount of water produced, same method but different molar ratio, we still have 0.500 moles of oxygen reacted. For every 3 moles of oxygen, we produced 4 moles of H2O. Are we following so far? Any questions? Okay, so far, really, we're just using mole ratios to find how much product is produced. We use a limiting reactant to do that. The last thing we need to do, we know we're going to use up all of the oxygen because that's the limiting reactant, but we know we're not going to use up all of the methanol. So we have to determine how many moles of methanol are reacted with oxygen. Then we can subtract that from the total amount and find the moles of methanol that are left over. So similar equation, we have 0.500 moles of O2 reacted. For every 3 moles of O2, we react 2 moles of methanol. So that means that we have 0.333 moles of methanol, CH3OH, reacted or used up. So then moles of CH3OH remaining that's not reacted, so the amount left over is the starting amount, so 1.500 moles, minus the amount reacted, 0.333. So then at the end of the reaction, we still have 1.167 moles of CH3OH present, because this amount of moles did not react with oxygen gas. Questions? Okay, I'll leave this up here for a minute, but we are at the end of class. So I will see you all on Friday. Don't forget your calculator and a pen or pencil.
send them an email to you?
Ooh, I forgot. What was it about again? We talked about it on Monday.
No,
I
it's okay.
forgot.
I'm just gonna be gone next week.
Oh yeah, okay. I will let you know. Let me write that on my actual to-do list. I don't forget. I'm sorry. Yes. No, just up to chapter 4. You're welcome. Hi.
Hi, I want to remind you about the
Yes.
Success Center.
You're good. I will drop it
Okay.
off early tomorrow, and then you'll just have any time on Friday. You can go and take it. It's
Okay.
just due at the end of the day. I know they close at 5, so you just want to make sure you give yourself enough time to do it.
Okay, thank you. And
You're
I also
welcome.
have another question. So since it's cumulative, is it kind of going to be split in half, like, or is it going to be like more of the new stuff, or is it going to be slightly like?
Yeah, just barely a little bit more of chapters 3 and 4. So
Okay.
not quite as much of chapters 1 and 2, which were on the first assessment, but still, like, there's 30 questions total. Maybe like 10 to 12 questions are on chapters 1 and 2.
Oh, okay.
And then the rest are on chapters 3 and 4.
Okay. Thank you.
You're welcome. Hi. What's up?
Are the questions on the exam going to be like math, just all the math, or is it going to be some definition?
There will be some like conceptual questions. Not all of them are math, but there is some math. You'll have like scrap paper to work through all the math problems, but they're still all multiple choice.
Okay.
Yeah.
Thanks.
You're welcome.